When a credit card is swiped at a terminal in a coffee shop, like an entire universe of computation happens in the roughly 800 milliseconds it takes for the machine to beep approve.
Oh, yeah. It's incredibly fast.
Right. And behind the scenes, that transaction data is routed to a server where this algorithmic model is, well, it's mapping the purchase against a high-dimensional vector space of your past behavior.
Exactly.
It's checking the geographical location, the velocity of recent transactions, typical vendor categories, and just thousands of other latent variables to determine the probability of fraud. And it happens with such mathematical precision and speed that from the outside, it is completely frictionless.
It looks completely invisible to the user.
Yeah, exactly. We look at the optimization of global power grids or, algorithmic high-frequency training or real-time medical imaging analysis, and we use a single, heavily burdened phrase to describe it all. We call it artificial intelligence.
And that phrasing right there is, it's the root of an enormous amount of structural confusion in the modern enterprise.
Oh, absolutely.
Because we use the term to describe this incredibly broad spectrum of computational systems. We treat everything from a simple, linear regression model to a multi-billion parameter neural network as if they are the exact same species of technology.
Right, like they're all just magic boxes.
Exactly. And if we're going to actually understand the mechanics of these systems, we have to stop treating the output as magic. We really need to start looking at the mathematical and, the infrastructural reality of how these models are built.
And that is the precise mission for this deep dive today. We are acting as your instructors to completely deconstruct Chapter 1 of the ISAC Artificial Intelligence Primer.
Yes, going right to the foundations.
Right. We're going to strip away the marketing gloss and build a rigorous foundational understanding of the architecture. So we're going to look at the hierarchy of data engineering required to make these models function, the specific historical bottlenecks, both in hardware and cognitive theory, that really define the field.
And of course, the architectural differences between machine learning, deep learning, and generative systems.
Exactly.
Because look, it's essential to start by defining the perimeter of what we're actually analyzing here. The AI pioneer, Marvin Minsky, he famously referred to AI as a suitcase term.
A suitcase term, yeah. I love that.
Right. It's this concept that has just been stuffed with dozens of disparate computer science disciplines, mathematical theories, and, engineering techniques over the last 70 years.
Just crammed in there.
Yeah. So when an organization claims they're, quote, deploying AI, they might be deploying natural language processing, computer vision, robotic process automation, or just basic predictive analytics.
Okay, let's unpack this suitcase then, because the ISACA primer fundamentally defines AI as techniques that equip computers to emulate human behavior. Basically, giving a machine the functional capacity to see, to hear, to speak, and to execute decisions based on environmental variables.
That's the baseline definition, yeah.
But to actually unpack Minsky's suitcase, we have to look at the architectural taxonomy. So figure 1.1 in the source material maps this out as a series of concentric circles, kind of like a set of nested subsets.
Right, or like Russian nesting dolls.
Exactly, Russian nesting dolls. So AI is the outermost boundary, the biggest doll, the entirety of the field. And inside that boundary, if you open it up, you have the first major subset, which is machine learning, or ML.
And the distinction between traditional software engineering and machine learning is, it's a total paradigm shift in how we approach problem solving.
How so?
Well, in deterministic traditional programming, human engineers explicitly write the logic. You define the rules, you input the data, and the system outputs the answer.
Right, it's very linear.
Exactly. But machine learning reverses that entirely. You input the data, and you input the desired answers, and the ML algorithm computes the rules.
Oh, I see. It's shifting from explicit instruction to, statistical inference.
Yeah.
Let's look at facial recognition as a functional example for this, because, traditional software is like a strict recipe. But you can't sit down and write deterministic code to define a human face.
No, it's impossible.
Right, you can't write an if-then statement that accounts for every variation in lighting or the angle, facial hair, bone structure. It would be endless.
So instead, in a supervised machine learning context, you feed the algorithm millions of labeled images.
Right, and the system iteratively maps the pixel values. It calculates the statistical correlations, the distance between the pupils, the geometry of the jawline.
And it autonomously develops a mathematical model to identify those specific patterns in novel, unseen data. It improves its performance autonomously over time, just through exposure to data. It's learning by tasting the food, so to speak, rather than following the recipe.
Okay, so that's the ML doll. But machine learning itself is a massive field, right? It contains everything from random forests to support vector machines.
Yeah, lots of techniques in there.
So if we move one layer deeper into our concentric circles, we open the next doll and hit a highly specialized subset of ML known as deep learning.
And this is where we transition from standard statistical algorithms to artificial neural networks.
The brain stuff.
Yeah, the brain stuff. When we talk about deep learning, we're talking about multi-layered architectures that are heavily inspired by the biological structure of the human brain.
But let's ground that analogy in the actual math for you listening, because it sounds a bit sci-fi. A neural network is fundamentally just a series of interconnected nodes, right? Organized into distinct layers.
Right, you have an input layer, several hidden layers in the middle, and an output layer.
Let's trace how data actually moves through that architecture.
Sure. So when raw input data, say the pixel data of an image we talked about earlier, when that enters the first layer, each node processes a fraction of that information.
Okay.
And the critical mechanism here is that the node applies a specific weight to the input. Yeah, a mathematical parameter that dictates the relative importance of that specific piece of data to the overall function.
Oh, I get it. So the node computes the weighted sum, passes it through an activation function to determine if the signal is, significant enough to transmit, and then fires that output to the next layer of nodes.
Exactly. It's a cascading system of feature extraction. So the first hidden layer might just recognize the basic edges of shapes.
Just lines and curves.
Right. But by the time that weighted data cascades to the fourth or fifth hidden layer, the network is assembling those edges into complex geometries, like the shape of a stop sign or the structure of a human eye.
And so the deep in deep learning literally refers to the number of these hidden layers between the input and the output.
Exactly. And the network learns by constantly adjusting those weights. If the final output is wrong, the system calculates the margin of error and propagates that error backward through the network.
Oh, that's backpropagation.
Yes, tweaking millions of individual weights by just fractions of a decimal point until the model mathematically converges on the correct output.
Which brings us to the final, innermost doll of our taxonomy, generative AI.
Sitting right at the center.
Right. This is a specific subset of deep learning. Most traditional deep learning models are discriminative, right? They're designed to analyze data and classify it.
Yeah, they tell you if an email is spam or if a tumor on a scan is malignant.
But generative AI models completely flip that architecture. They are trained on such staggeringly vast data sets that they don't just map the boundaries between classifications, they actually map the underlying distribution of the data itself.
Right, and because they understand the complex statistical distribution of the training data, they can synthesize entirely new data points that fit perfectly within that distribution.
They generate novel text, or photorealistic images, or functional code based on high-dimensional probability.
Yeah, they aren't retrieving stored files. I think that's a huge misconception. They are dynamically calculating the most statistically probable next token or pixel based on whatever prompt you give them.
Okay, so the taxonomy is clear. Let's recap it for you. AI is the overarching emulation of human behavior. Machine learning gives systems the ability to learn rules from data. Deep learning utilizes multi-layered neural networks for complex feature extraction. And generative AI uses those deep networks to synthesize novel outputs.
And understanding the taxonomy is critical. It fundamentally alters how you evaluate the technology out in the real world.
Why is that?
Well, it allows you to ask the right structural questions. When a vendor pitches an AI solution to you, you need to know exactly which layer of that taxonomy they are operating in.
Because the requirements are different.
Completely different. The computational requirements, the infrastructure demands, and frankly, the failure modes, they are radically different for a basic ML classification algorithm compared to, say, a complex generative neural network.
Right. But, regardless of whether you're deploying a simple regression model or a massive generative network, none of those algorithms can function without a highly rigorous underlying architecture.
No, they absolutely cannot.
The models themselves are just engines. They require an immaculate fuel supply. So to understand how that infrastructure is actually built, the ISACA primer references this really cool concept called the data science hierarchy of needs.
Yeah, this framework was originally adapted by data scientist Monica Rogati, and it's modeled on Maslow's psychological hierarchy of needs.
Oh, right, like food and shelter at the bottom, self-actualization at the top.
Exactly. The core premise is structural dependencies. You cannot achieve the highest level of systemic capability, which is the AI model at the top, if the foundational layers of data infrastructure below it are unstable or fragmented or just missing entirely.
And the reality of data engineering is often obscured, I think, by the hyper-focus on the models themselves. Everyone wants to talk about the AI.
Oh, for sure. The models get all the glory.
Right. So let's break down this pyramid from the absolute foundation. The bottom, widest layer of the hierarchy is collect. Because before you can train anything, you must establish the telemetry to gather the raw material.
Right. We're talking about application logging, physical IoT sensors, user interaction data, maybe ethical web scraping.
And the sheer volume of data generated at this layer is staggering. But more importantly, it is highly chaotic.
Yeah, it's a huge mess. It's a mix of structured databases, semi-structured logs, and completely unstructured text or video files.
Which immediately forces you into the second layer of the pyramid, right?
Oh.
Store and move.
Yes, and this is the critical bottleneck for most enterprise systems today. You have to physically move that massive volume of data from the collection points into a centralized repository, like a data lake or a data warehouse.
And this requires robust ETL pipelines, right? Extract, transform, and load. You are establishing the digital plumbing.
That's a great way to put it.
And if those pipelines are brittle, if they suffer from high latency, or if they drop packets during the transfer, then everything built above this layer is inherently compromised.
Exactly. Once the data is successfully stored and it's moving reliably, then you ascend to the third layer, which is explore and transform. And honestly, this is where the grueling reality of data science actually lives.
Because raw data is inherently flawed.
So flawed. It contains missing values, corrupted formats, duplicate entries, extreme anomalies.
Right. Like if you're pulling temperature data from 1,000 industrial sensors and one sensor shorts out and just starts reporting negative 500 degrees.
Yeah, you have to detect and handle that anomaly. You have to scrub the errors, normalize the formats, and impute missing values so that the data is mathematically cohesive.
And that normalization prepares the data for the fourth layer, which is label and aggregate.
Yes. Here you're defining the metrics that actually matter and segmenting the data for specific training purposes.
Like if you're training a supervised computer vision model to detect defects on a manufacturing line, this is the stage where human annotators often have to painstakingly draw bounding boxes around thousands of images of microscopic fractures.
Oh yeah, just to create a verified ground truth training set. It's very labor intensive.
Then and only then do we reach level 5, which is learn and optimization.
We're finally at the stage where machine learning algorithms enter the environment.
The data is clean, it's labeled, it's flowing reliably. Data scientists can now begin training models, running A/B experiments, executing hyperparameter tuning to, dial in the mathematical precision of the algorithm.
And sitting at the absolute apex of this pyramid is level 6, AI.
The top of the pyramid.
The deployment of deep learning and generative AI. This is the culmination of the entire architectural stack, where the system is finally capable of executing complex, autonomous pattern recognition and generation.
Okay, but I think we need to examine a very common friction point here. Let me push back a bit. Because there is a massive temptation, especially right now, for organizations to try and bypass this entire pyramid.
Oh, I see this all the time.
Right. If I'm a startup or an executive at a big company, I might look at this and say, I don't want to spend 2 years and millions of dollars building ETL pipelines and normalizing data lakes. Can't I just purchase a license for an off-the-shelf generative AI model, integrate it via an API, and jump straight to the apex of the pyramid?
And that right there is the most common architectural mistake occurring in the industry today.
Really?
Absolutely. Because AI is basically the self-actualization of data. The problem with simply bolting an advanced AI model onto the top of a dysfunctional data infrastructure is that an AI model operates as a computational amplifier.
It amplifies whatever you feed it.
Exactly. It has no independent understanding of context or reality. It only knows the data it processes.
So if your foundational collection methods are flawed, or if your ETL pipelines routinely drop critical telemetry, or if your anomaly detection fails to catch corrupted inputs,
then the AI model will simply process that garbage data and confidently output deeply flawed, high-speed, automated decisions. Every time you read about a catastrophic AI failure in the news, view it through this lens.
it's the systemic scaling of bad data.
Yes. If a massive retail logistics system hallucinated a critical supply chain failure, or an automated trading desk executed a massive sell-off based on a false signal, The root cause is rarely a failure in the neural network at the apex.
Right. The failure almost always resides in the lower levels of the pyramid, like a dropped table in the storage layer or a corrupted feed in the collection layer. You cannot build a sophisticated algorithmic structure on a foundation of unverified, fragmented data.
You really can't. The AI is entirely captive to the integrity of the data pipelines beneath it.
Wow, okay. That is a crucial takeaway for you listening.
And, establishing that kind of rigorous, highly structured infrastructure didn't happen in a vacuum. The deep neural networks we deploy today are the result of decades of theoretical evolution, hardware scaling, and cognitive research.
It took a long time to build this mountain.
To truly understand why the technology operates the way it does, we have to trace the historical continuum. We have to travel all the way back to the 1950s.
Ah, the 1950s, the absolute bedrock. I mean, the concept of mechanized logic existed earlier, obviously, but the formal inquiry into machine intelligence was crystallized by Alan Turing. In 1950, he published Computing Machinery and Intelligence, and Turing bypassed the whole philosophical trap of trying to define the exact biological nature of human consciousness. Instead, he approached intelligence as a strictly behavioral and computational output.
Turing understood that debating whether a machine could, quote, feel or possess a soul was just an endless philosophical quagmire. You'd never get anything built.
Right, unanswerable.
So he designed a purely pragmatic heuristic, which he called the imitation game. And we now universally know this as the Turing test.
Okay, so the premise was operational. If a human judge communicating exclusively via a text interface could not reliably distinguish between the conversational output of a machine and the conversational output of a human, then the machine must be considered operationally intelligent.
It divorced the concept of intelligence from biological hardware entirely, and that operational focus became the mandate for the whole field.
And then 6 years later, in 1956, the term artificial intelligence was formally coined at the Dartmouth Conference. Researchers like John McCarthy and Martin Minsky convened with the explicit goal of mapping human cognitive processes to computational logic.
The optimism of that Dartmouth conference is literally legendary in computer science.
Oh, they thought they'd solve it in a few months.
Exactly. They genuinely believed that if they just spent a summer meticulously codifying the rules of human logic, they could solve the core challenges of machine intelligence. They viewed intelligence as just a series of solvable symbolic equations.
Here's where it gets really interesting, though, because that initial surge of optimism led to some fascinating early experiments. And the most revealing of those occurred in the 1960s at MIT.
Yes, with Joseph Weizenbaum.
Right. Weizenbaum developed a natural language processing program called ELIZA. And ELIZA was specifically designed to simulate a Rogerian psychotherapist.
And for those who don't know, a Rogerian approach is where the therapist largely reflects the patient's statements back to them as open-ended questions.
Right. But the underlying mechanics of ELIZA are critical to analyze here, because ELIZA possessed no neural networks, no latent space, and definitely no statistical understanding of language.
None whatsoever. It was a deterministic program built entirely on basic string manipulation and pattern matching. It just scanned the user's input for specific predefined keywords.
It was an incredibly rigid script. It's like the world's first customer service phone tree. If you typed, I am feeling stressed about my father, the program would parse the string, flag the keyword father, access a lookup table of pre-written templates, and output a concatenated response like, tell me more about your father.
And if it couldn't find a keyword at all, it relied on generic fallback phrases like, please go on, or I see.
Operationally, it was exceptionally rudimentary. But the psychological impact of that rudimentary script was unprecedented. I mean, it's wild.
Yeah.
People interacting with ELIZA began to attribute deep empathy, understanding, and complex internal thought processes to the machine.
They really did.
They would pour their hearts out, confessing deeply personal secrets to a glorified script that was doing nothing more than rearranging the syntax of their own sentences. It's like forming a deep emotional bond with a magic 8-ball.
It really is. And this phenomenon became known as the ELIZA effect. Weizenbaum himself was deeply disturbed by it.
Oh, he hated it.
Yeah. His own secretary, who was fully aware of the underlying source code and the complete absence of any cognitive function in the machine, she actually asked Weizenbaum to leave the room so she could converse with the program in private.
Yeah, it's just mind-blowing.
But the ELIZA effect is a critical concept in the ISACA primer because it highlights a permanent, hardwired vulnerability in human cognition.
Go on.
Well, humans are biologically primed for social interaction. We possess a theory of mind, That's the evolutionary capacity to attribute mental states, beliefs, and intentions to others. And what ELISA proved is that our theory of mind is highly susceptible to hijacking.
We just want to believe.
We will involuntarily project consciousness, intent, and empathy onto an inanimate system the moment it exhibits even a superficial simulation of conversational reciprocity.
Wow. And this is a massive architectural warning for the systems we deploy today.
Yeah.
When you're using a modern generative network and it outputs a response that says, I understand your frustration, I am happy to assist you, it is fundamentally executing the exact same mechanical illusion as ELISA.
Exactly the same illusion.
It's calculating the most probable syntactic output based on its training distribution. It does not possess an internal state of happiness, nor does it comprehend the concept of frustration. But because the output perfectly mimics the syntax of human empathy, the ELISA effect guarantees that humans will implicitly trust the system as if it were a cognitive peer.
We are wired to be fooled by it. And while ELISA demonstrated the profound power of simulated language, the broader ambitions of the 1960s AI researchers hit a brutal physical bottleneck.
The hardware just wasn't there.
Programs like ELISA operated in highly constrained, text-based environments. But when researchers attempted to scale algorithms to tackle complex real-world problems like machine translation or computer vision, the physical hardware of the era completely failed them.
The theoretical mathematics of artificial intelligence were writing checks that the physical reality of vacuum tubes and early transistors simply could not cash. The algorithms required a volume of sequential processing and memory allocation that was, frankly, physically impossible on machines that were the size of an entire room.
And this hardware bottleneck forces us to examine the physical laws that govern computation, specifically Moore's law.
Gordon Moore, 1965.
Right. In 1965, he posited an observation that would basically define the economic and architectural trajectory of the whole digital age. He stated that the number of transistors that could be manufactured on a single integrated circuit would double approximately every 2 years.
It's the principle of exponential miniaturization. A transistor is essentially a microscopic switch that controls the flow of electrical current, right? Representing the ones and zeros of binary data.
Correct.
And by continuously shrinking the physical geometry of those transistors, engineers could pack exponentially more computational power into a smaller physical footprint, which simultaneously reduced the cost and increased the processing speed.
And Moore's law is the physical foundation of the entire AI revolution. I mean, the evolution from room-sized mainframes to the massive parallel processing capabilities of modern graphics processing units, or GPUs, is entirely dependent on the relentless, decades-long execution of Moore's law.
GPUs are huge for this.
They possess thousands of smaller, highly efficient cores designed to process multiple streams of data simultaneously, which happens to be the exact computational architecture required to calculate the millions of weighted matrices in a deep neural network.
But the relentless progression of Moore's law was not fast enough to save the early pioneers. I mean, by the 1970s, the discrepancy between the massive, unfulfilled promises of human-level machine intelligence and the severe limitations of the hardware became impossible to ignore. Algorithms just couldn't scale. Machine translation projects failed spectacularly.
And the failure to deliver on those high-profile promises resulted in a devastating collapse in funding and institutional support. Government agencies like DARPA, which had heavily subsidized early research, they just withdrew their capital.
The money dried up.
Completely. This era is historically referred to as the AI winter. It was a period of intense skepticism where the very term artificial intelligence became professionally toxic in computer science departments.
The field contracted massively, but the underlying research continued to evolve in the background, leading to a resurgence in the 1980s, which was kind of the next summer, right?
Yeah.
Instead of attempting to build general human-like intelligence, researchers pivoted to highly specialized, domain-specific architectures known as expert systems. Credit there goes to Edward Feigenbaum.
Right. Expert systems basically abandoned the attempt to simulate broad cognitive function. Instead, they focused on codifying the explicit knowledge and decision-making rules of human specialists in very narrow fields.
So they were essentially massive, highly complex decision trees.
Exactly. If you wanted to build an expert system for medical diagnosis, you would interview top physicians, extract their diagnostic heuristics, and program a vast architecture of if-then rules to replicate that specific decision matrix.
It was a shift from attempting to build a general mind to building a highly efficient, specialized calculator. But wait, I want to pause and look at the physical trajectory of hardware again.
Sure.
Because the ISACA text explicitly notes a looming architectural boundary. The warning that Moore's law could reach its absolute physical limits by the year 2030. So, if Moore's law is dead by 2030, does the AI revolution just hit a physical brick wall in a few years?
That is one of the most critical structural challenges facing the industry today. Moore's law, remember, is not a law of physics. It's an observation of engineering economics. And we are rapidly approaching the atomic threshold.
How small are we talking?
Transistors are now being manufactured at scales measured in single-digit nanometers. When you slice silicon that thin, you encounter the laws of quantum mechanics.
Right, quantum tunneling. The barriers between the components become so infinitesimally small that electrons simply pass right through them.
Yeah, rendering the transistor incapable of holding a reliable binary state. You literally cannot make the switch any smaller without the physics breaking down.
So what happens then? What are the implications of that physical limit for AI?
Well, over the last decade, the default solution to improving the performance of an AI model was brute force. If a neural network wasn't accurate enough, researchers simply added 100 billion more parameters, purchased 10,000 more GPUs, and utilized massive amounts of electrical power to brute force the training process.
It's been a strategy of scaling compute over algorithmic efficiency.
Exactly. And if Moore's law physically terminates, that strategy collapses. You can no longer rely on the hardware automatically getting twice as fast and twice as cheap every 2 years.
Wow. So the end of Moore's law forces a radical paradigm shift in AI research.
It demands a transition from brute force scaling to extreme algorithmic efficiency. Researchers will have to design models that achieve high performance with significantly fewer parameters.
It also accelerates the demand for entirely novel hardware architectures, I'd imagine, like neuromorphic processors that physically mimic the analog structure of biological synapses, or, the eventual integration of quantum computing to handle those complex, multidimensional matrices.
Right. The end of the exponential hardware curve is a forcing function for architectural innovation.
But historically, the steady march of Moore's law did eventually provide the necessary compute power to achieve the milestones the early pioneers dreamed of. As we moved into the late 1990s, the hardware finally caught up to the algorithmic theory, and it led to a massive, highly public turning point that changed how humanity viewed machines.
Yes. The most culturally significant of those breakthroughs occurred in 1997 when IBM's Deep Blue supercomputer defeated the reigning world chess champion, Garry Kasparov, in a 6-game match.
This was an absolute watershed moment. Chess had long been considered the ultimate crucible of human intellect, a game requiring not just calculation, but deep strategy, intuition, and, psychological resilience.
The soft variables of human strategy.
Exactly. For a machine to defeat a human grandmaster, it shattered a massive psychological barrier regarding the limits of computation. And it sparked a ton of AI investment in things like finance and climate modeling.
But to understand the significance, we have to look at how Deep Blue operated. It was the ultimate triumph of symbolic AI and massive search architecture. Deep Blue did not learn to play chess via neural networks.
It didn't.
No, it utilized a brute force heuristic search algorithm called Minimax, combined with highly sophisticated alpha-beta pruning. It could evaluate 200 million chess positions per second, mathematically calculating the optimal move by projecting millions of potential future board states.
Wow. So Deep Blue proved that a machine could entirely master a complex, closed system of logic. But chess is a perfect information game. The rules never change, the board is finite, and there is no hidden data.
Right.
The real world is not a closed system. The real world is analog, it's noisy, and it's chaotic.
Which is why the subsequent milestones focused on moving machines out of closed systems of logic and into the messy reality of sensory perception. In the late 1990s, software like Dragon, naturally speaking, pioneered continuous speech recognition.
Oh, I remember that software. That was a profound shift. Analyzing human audio requires processing an analog signal filled with variance. You have different accents, background noise, fluctuations in cadence and pitch.
Exactly. And Dragon utilized hidden Markov models, which are complex statistical architectures, to map acoustic signals to phonetic probabilities. It wasn't calculating a deterministic board state like Deep Blue. It was executing highly complex statistical inferences to perceive and transcribe the physical world.
We moved from the pure calculation of Deep Blue to the sensory perception of Dragon.
And that progression from calculation to perception set the foundational stage for the explosion of modern AI. because once machines could perceive the world, researchers began designing architectures that could actively synthesize new realities.
Which brings us to 2014 and the introduction of a revolutionary architecture by researcher Ian Goodfellow, Generative Adversarial Networks, or GANs.
GANs completely shifted the paradigm. This is where we cross the threshold into the modern era of generative AI.
The architecture of a GAN is essentially two distinct neural networks locked in a mathematical cage match, constantly optimizing against each other.
Yes, the system consists of a generator network and a discriminator network, and their objectives are diametrically opposed.
Let me use an analogy here. It's like an art forger, which is the generator, and a detective, the discriminator, locked in an endless training montage.
That's a perfect way to visualize it.
So the generator's sole objective is to synthesize artificial data, say a photorealistic image of a human face that is completely indistinguishable from real data. And the discriminator's sole objective is to analyze data and correctly catch the fakes.
The interplay between the two is a zero-sum game. The generator creates an image, essentially mapping random noise into the latent space of facial features, and passes it to the discriminator. Initially, the generator is terrible at this. It just outputs static.
And the discriminator analyzes the static, correctly flags it as a forgery, and rejects it.
But the crucial architectural component is the loss function. When the discriminator rejects the image, it calculates the specific mathematical gradients of why the image was rejected, and it backpropagates that exact error signal to the generator.
So the generator learns from it.
Exactly. It uses that precise mathematical feedback to adjust its internal weights and biases, slightly improving its ability to mimic the structural distribution of a real face.
It's a continuous automated training loop. The forger gets mathematically better at painting, which forces the detective to become highly sensitive to microscopic errors to catch the increasingly sophisticated fakes.
And the discriminator's improved detection protocols are fed back to the generator, forcing the generator to achieve an even higher level of synthesis. This adversarial loop continues for millions of cycles until the system reaches a mathematical equilibrium.
And at that point of convergence, the generator has mapped the target distribution so perfectly that it synthesizes images of human faces with flawless structural geometry, lighting, and texture. The discriminator is effectively reduced to guessing at random because the statistical distribution of the fake data is indistinguishable from the real data.
GANs proved that neural architectures could master the generation of high-fidelity, open-ended media. It's the underlying mechanism that accelerated the development of high-quality images, video, realistic voice synthesis, and the highly sophisticated text-to-image models that define the current landscape.
It's incredible. And if we trace that historical through line, the trajectory of the capability is just profound. In 1997, Deep Blue proved that algorithms could master the calculation of perfect information logic. The speech recognition models of the 90s proved algorithms could master the perception of noisy analog environments. And the advent of GANs proved that algorithms could master the synthesis and generation of novel, highly complex realities.
We moved from calculation to perception and finally to generation.
Which forces us to ask a deeply fundamental question about the end state of this technology. If we're moving from basic data classification to the flawless, automated synthesis of human-like creativity and reasoning, what exactly are we trying to build? Are we just writing code, or are we trying to recreate the mind itself?
And that transitions us to the final section of the ISACA primer, which explores the interdisciplinary overlap between artificial intelligence and cognitive science.
Because the deeper we push into complex neural architectures, the more we realize that AI cannot exist purely as an isolated subfield of computer science. It overlaps deeply with cognitive science and social cognition.
To build a system that can simulate reasoning, you have to understand the foundational mechanics of how biological reasoning actually functions.
So what does this all mean for cognitive science? Cognitive science is the interdisciplinary study of the mind, right? Philosophy, psychology, neuroscience, linguistics, anthropology. It analyzes how the human central nervous system processes perception, thought, action, and how it utilizes stored information.
AI researchers heavily borrow from these disciplines to design the architecture of neural networks. We look at the biological visual cortex to design the convolutional layers of computer vision models. We study the cognitive structures of human linguistics to design the attention mechanisms of large language models.
But we have to strictly define the divergence in their goals. The ultimate goal of cognitive science is analytical. It seeks to understand the true fundamental principles of biological intelligence. But the goal of AI is synthetic. It seeks the simulation of that human intelligence by computerized systems that can self-correct.
This distinction is critical as the industry pushes toward the theoretical concept of artificial general intelligence, or AGI, and ensuring those systems are implemented safely. AGI is the hypothesis of a highly autonomous system that possesses the capacity to understand, learn, and apply knowledge across an infinite range of completely novel tasks.
We're basically reverse engineering the human brain using math. But I have to ask, are we actually understanding intelligence or just faking it really well?
That is the profound difference between a machine that can simulate a behavior and one that understands a behavior. This is the ultimate philosophical hurdle of AI. The models we possess today, regardless of their parameter count or their ability to generate complex code and photorealistic art, they do not understand the world.
Right. A large language model processing a physics equation does not comprehend the physical reality of gravity. It is executing highly complex, high-dimensional statistical pattern matching based on its training data.
Exactly. By attempting to engineer an artificial mind, we aren't just making computers smarter. By studying human cognitive science alongside AI, we are being systematically forced to rigorously define what constitutes human consciousness, intuition, and comprehension. We cannot map the architecture of intelligence if we cannot define its parameters.
Wow. It is a phenomenal mirror reflecting our own cognitive structures back at us. We have covered an immense amount of architectural ground today. Let's synthesize the core components of this deep dive for you listening.
Mm.
We started by unpacking the suitcase term, establishing the critical nested structural differences between the hard-coded logic of traditional software, the statistical inference of machine learning, the multi-layered neural architectures of deep learning, and the probabilistic synthesis of generative AI.
We then mapped the physical infrastructure required to support those models, utilizing the data science hierarchy of needs. We established that the deployment of advanced AI at the apex of the pyramid is physically impossible without the rigorous execution of data collection, ETL pipelines, anomaly detection, and data normalization at the base.
We trace the historical evolution from Alan Turing's behavioral theories through the psychological illusions of ELIZA and the funding collapse of the AI winter. We examine how the exponential scaling of Moore's law eventually provided the hardware necessary to transition from the symbolic logic of Deep Blue to the analog perception of speech recognition, and finally to the adversarial generation of GANs.
So the next time you use a chatbot or read a headline about AI, you aren't just seeing magic. You're seeing the top of the data pyramid built on decades of hardware evolution and cognitive science.
I want to leave you with a final thought to ponder as we close out. We learned about the ELIZA effect earlier, right? How eager we are to project a soul into a simple script. As GANs make AI output indistinguishable from human creativity, and as Moore's law pushes us to limits by 2030, the greatest challenge in the future won't be teaching machines to think like humans. It will be remembering that they're still just machines. If a machine can perfectly simulate empathy, it doesn't matter if it's real.